All right, let's dive into the world of telecommunications and networking. If you're studying for an exam, or you're just curious about how we all stay connected, you've come to the right place. We're going to build this whole world from the ground up, starting with the very basics.
So, here's our game plan. First, we'll look at the actual physical highways our data travels on. Then, we'll get into the traffic rules that keep all those connections from turning into a massive jam. After that, we'll zoom out and see how networks are laid out, we'll explore the magic of going wireless, and finally, we'll put it all together by tracing a single phone call from the second you hit dial.
Okay, first things first. Before a single bit of data can go anywhere, it needs a road to travel on, right? This is our communication highway, and it is literally the physical foundation for everything else we're going to talk about.
I mean, it sounds almost too simple, but have you ever stopped to think about how your message physically gets from your device to someone else's? Well, the answer lies in what we call the transmission medium, the actual path it takes.
You know, it really all boils down to two main ways a message can travel. It's either guided, meaning it's sent through a physical wire or a cable, or it's unguided, where it just travels wirelessly through the air as a wave. Simple as that.
Now this table right here, this is your exam cheat sheet for guided media, so really pay attention. You've got twisted pair. It's cheap, but it's slow and loses signal. Then there's coaxial cable, which is a step up, but fiber optics, that's the real game changer. It gives you incredible bandwidth and the signal barely degrades. But here is the killer feature, and you need to remember this. It sends data using light, not electricity. That means it's completely immune to electromagnetic interference, or EMI. That is a massive, massive advantage. So, the main takeaway here is pretty straightforward. The highway you pick, whether it's copper wire, a fiber optic strand, or just the open air, is what sets the ultimate speed limit and really determines how reliable your connection is going to be.
Okay, so we've got our physical highways. But with billions of devices all trying to talk at once, how do we stop it from becoming total gridlock? Well, that's where switching techniques come in. These are the rules of the road for our data.
And there are really two main ways to handle traffic. First, there's circuit switching. This is like the old telephone system. It gives you your own, private, dedicated line for the entire call. It's super reliable, but not very efficient. Now, the internet uses something totally different, packet switching. It chops your data into these little packets, sends them all out to find the fastest routes, and then puts them all back together on the other side. It's a way more efficient way to share the network.
So, what if you want the best of both worlds? What if you want the reliability of a dedicated line, but with the efficiency of a shared network? Well, that is the genius idea behind a virtual circuit. It's a really clever way to create a logical private path that just runs on top of the shared physical network.
And this image shows you exactly how it works. That big cloud in the middle, that's the shared network. Now, each connection point gets a unique address called a Data Link Connection Identifier, or DLCI. So even though everyone's data is flowing through the same switches, that DLCI acts like a little mailing address on every single packet, making sure it follows the right virtual path and gets exactly where it needs to go.
So, just think of switching as the brains of the network operation. It's the whole system of traffic cops that directs our data, either by giving us a private lane or by expertly weaving millions of little data packets through a bustling digital city.
All right, we've laid the roads and we've set the traffic rules. So now let's zoom out a bit and look at how we organize all these connections into actual networks, from what's in a single office to what spans the entire globe.
So the first way we sort networks is by scale. A local area network, or LAN, is what you probably have at home or in your office. It's super fast, but it's small. When you need to connect those LANs across the city or even across the world, you use a wide area network, or WAN. And really, the internet itself is the ultimate WAN.
Okay, but inside one of those networks, how are all the computers and devices actually laid out? That's called topology. A bus topology is kind of like one main street where everyone connects. A ring is where data flows in a circle from one device to the next. But by far the most common layout you'll see, especially at home, is the star topology. That's where every single device connects to a central point, like your Wi-Fi router.
So a good way to think about it is this. Scale, LAN versus WAN, tells you if you're building a neighborhood or an entire country. And topology, that's the city map you're using to lay out all the streets and all the houses.
So far, we've been pretty focused on wires and cables, but let's be real. The modern world absolutely runs on mobile. So let's unpack the revolutionary idea that makes it all possible, the cellular concept.
Honestly, this might be the single most important idea in mobile communication.
The first idea people had was to try and cover a whole city with one gigantic, super powerful radio tower. It was a terrible idea. It was inefficient and could only handle a few calls at once. The cellular concept completely flipped that on its head by using lots of low-power transmitters, with each one covering just a small area or cell.
And this is where the real magic happens. See how the shaded cells are all pretty far apart? Well, they are all using the exact same radio frequencies. This is called frequency reuse, and you absolutely, positively need to know this for your exam. By making sure the cells that share frequencies are spaced out, their signals don't interfere with each other. This one brilliant idea is what lets a limited number of radio channels support millions and millions of users all at the same time. But what happens when you move from one of those cells to another? Like when you're driving, that's where something called the handoff comes in. As you're moving, your phone is constantly checking the signal strength from all the nearby towers. The second you start leaving one cell and entering another, the network seamlessly hands off your call to the new tower, and you don't notice a thing. This is the magic that makes mobile, well, mobile.
So if you remember one thing from this section, make it this. The entire mobile revolution was built on one simple, powerful principle: dividing big areas into small cells and then cleverly reusing the same frequencies over and over again.
Okay, deep breath. We've covered the physical media, the traffic rules, network structures, and the wireless concept. Now, for the grand finale, let's put all of these pieces together and trace the entire journey of a mobile phone call, from start to finish.
But first, a super quick history lesson. 1G in the 80s let us make calls on those giant brick phones. 2G was a huge leap. It went digital and gave us the magic of texting. 3G was our first real taste of the mobile internet. 4G LTE is what made streaming video in your hand possible. And now 5G is connecting everything with almost zero delay.
Okay, listen up, because this is a huge point for any exam: the digital handshake. Before you even say hello, this 4-step dance happens in the blink of an eye. Step 1. Your phone yells out for access on the Random Access Channel, or RACH. Step 2. The network hears it and replies on the Access Grant Channel, the AGCH. Step 3. On a special control channel, the SDCH, the network runs a security check to make sure you're a real subscriber. And finally, once you pass, the network gives you a traffic channel, the TCH, and your conversation can actually begin. So it's request, grant, authenticate, connect, all in an instant.
All right, let's wrap this all up. Here are the absolute must-know points for your exam. First, know the difference between guided and unguided media. And remember that fiber optics is the king of cables. Second, know that circuit switching reserves a path, like old phones, while packet switching is for the flexible internet. Third, the absolute key to cellular is frequency reuse. And finally, memorize that 4-step handshake for a mobile call: RACH, AGCH, CDCH, and finally TCH. Got it?
You know, we've gone from a simple copper wire to basically a global wireless brain. Today, 5G is connecting our cars, our homes, and our cities. So I'll just leave you with this thought. As we keep pushing what's possible, what on earth will the next generation of networking be able to do? Thanks for digging into all this with me.